All right, so asking the question, how do two subpopulations compare? All right, I see down there it says key concept, says the way we answer these types of questions is obviously going to collect samples from both subpopulations, okay? And then we perform the inference testing on those samples and make conclusions about mu sub 1 minus mu sub 2. So mu sub 1 minus mu sub 2. Mu sub 1 is the mean of population 1. Mu sub 2 is the mean of population 2. Okay. If that difference is equal to 0, that means the two were the same thing, weren't they? So there would be no difference. Okay. Most likely, okay, those will be different values, and we'll be able to make a conclusion then based on these samples. It says in order to do this, we need the following stuff. Okay, it says x sub 1, comma x sub 2, comma dot 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 x sub m is a random sample from a distribution with mean. This should be a subscript of a 1. Mu sub 1 in variance sub 1. Okay. Now it's kind of a messy looking way that we write variance, because variance is sigma squared, right? Okay. And because we're going to have two variances throughout these problems, because we're going to have two samples, we need subscripts. So we look at that, it says variance squared sub 1. It looks like that 2 and that 1 are stacked on one another. Understand that subscript of 1 is just an identifier. It's like a last name type thing. So we can differentiate that it is the different variance than variance for sample 2 here, or subpopulation 2. Says y sub 1, comma y sub 2, comma y sub m is a random sample from a distribution with mean mu sub 2 and variance sub 2. Okay, now as you go through this and as you look through different texts, they will use like different notation for the first sample. Instead of using x's and y's, they might use something completely different. I'm going to use x's and y's. I think it makes most sense. But if you're working in another textbook, they might just redefine these sample variables. Okay, not a big deal. Third one says that x and y samples are independent of one another, meaning that an individual out of sample x cannot be in sample y. If you're in this, if we're looking at how well this class is doing, if you're in this class, okay, you cannot be in 7th period. Does it make sense? Okay, if you're in 7th period, you cannot be in this class. Something that I will probably investigate at the end of the year is I will actually go through this stuff, because I'm interested in seeing the differences between students that were fully online versus the students that were fully in class. And I'll do some confidence intervals on those things to see was there a statistical difference. Okay, was there a change in because of the mode of disseminating information to them? Did that hamper their grade or increase their grade or whatever? Okay, so says the best estimate for mu sub 1 minus mu sub 2 is naturally, as we've seen elsewhere, going to be x bar minus y bar. Okay, because we don't have, remember, we're not going to look at the population, because we won't have the populations are going to be too big for us, right? So we're pulling in little samples out of those populations and look at those samples. Okay, now when I do this at the end of the year, I'll have the population, so I could do it with the population. But we are going to do it with samples because populations are too big. So mu sub 1 is the mean of population 1. Okay, x bar is the mean of the samples that came from population 1. Okay, everybody? Okay, mu sub 2 is mean of population 2. Y bar, capital Y bar, is the sample mean that came from that population. Okay, subtract them. It's the difference between the corresponding sample means. So we must standardize this estimator So we need expressions for the expected value and the standard deviation. All right, this stuff here, this is exactly the same. It's a little bit extended because obviously we're looking at two samples now, but it is very similar to the formulas that we saw when we dealt with doing this for one sample. Okay. Basically, what we come up with is that the standard deviation of the difference in sample means, okay, is equal to this. Okay. So now the notation, it gets messy looking here. Okay, and this scares people. If anybody been in physics? Nobody's taking physics? Okay. So I always compare it to physics because when we get into physics, there's a lot of different formulas and variables, and a lot of those formulas and variables use the same letters over and over and over again. So they start putting subscripts on them, and that just looks odd. Like it's something we haven't been working with very much, or we haven't seen, we're not familiar with it. So it scares people, and then they withdraw from it because it scares them. Okay, just understand that 2 right there where my cursor is just saying that we're talking about the variance from the second subpopulation. Okay, this is the variance that comes from the first subpopulation. Is that okay with everybody? Blaze? So the M is how big the sample was. M is how big the sample was for that first subpopulation. Okay? So if we're talking about comparing these two classes, first and seventh period, maybe M is the size of first period. Okay, and about 21 of us in here. Okay? And N would be the size of seventh period. Is that going to make sense? Okay? It's how big my samples are. All right. Now, because we're trying to estimate the population, if we don't know the population standard deviation, if that's not given to us, then what is a good replacement for population standard deviation if we don't know it? The sample standard deviation. Okay, so we could replace that sigma squared with S squared. Okay, so the sample variance is a great estimator for the population variance. Okay, or I look at that as standard deviation. Okay, and then we'll square that to get the variance. But so that could be sigma or that could be S. All right. So the sample variances must be used to estimate this when the population variances are unknown. That's what that bullet right there is talking about. So this is kind of what's happening here. We're taking a population. So overall, we've got this entire, so this green box would be maybe a greater population. We're going to take these subgroups, these two blue subpopulations, and we're going to find samples out of the first one. We'll take samples out of the second one, and then we look at their differences. Does that make sense? Okay, and we start subtracting those differences. Okay. We keep doing that all the way through, and now we have a cluster of sample differences, okay, sample mean differences, that we can put confidence intervals to. Okay. So here's how we're going to do this. Now, there's a lot of stuff here that I don't know that it has to be written down directly. So if both population distributions are normal, both X bar and Y bar have normal distributions. Okay, so I don't know that you need to write that down because that's something we've already talked about when we worked on confidence intervals for mu when sigma was known. Okay, go back to 8.1. That was a condition in 8.1 about finding a confidence interval for mu when sigma was known. Okay, so up here you see that I'm now talking about mu1 minus mu2 when sigma 1 and sigma 2 are both known, right? Okay, so in 8.1 it was just like looking at just mu sub 1 and sigma sub 1. Okay, so this condition has to be true. Okay, we have to have populations that are normal. Okay, it says independence of the two samples implies that the two sample means are independent of one another. It says M is the sample size of X and N is the sample size of Y. So we've already talked about that. Okay, has to be independent. Okay, so one of the questions at the beginning was, how do I compare like a medicine, the effects of a medicine on an adult group versus a child group? Okay, well, can a child be an adult, and can an adult be a child? Those are independent groups, correct? There's no overlap. Okay, so that's got to be key here. Third bullet says the difference x bar minus yy is normally distributed with expected value mu1 minus mu2 and standard deviation sigma sub x bar minus y sub, or x bar minus y bar. Okay, so we need to be able to standardize things. Okay, so this is, and I'm just going to go back to 8.1 real quick just to show you the comparison. When I wanted to find the z-score back in 8.1, we took the sample mean minus the population mean, okay, divided by sigma, okay, which is the standard deviation, divided by a square root of n. Okay. Is that right with everybody? Remember doing that? This thing is the same idea. Okay. That was the x bar. Okay. This was minus the mean. And now I've got this written as, so it's variance squared, but in the previous slide, and it's because of the summation, if I take a square root of variance, doesn't it just give me sigma? So that's where in 8.1, the reason people might ask, well, this one doesn't have a radical around this sigma here, right? Well, it would if it was squared. Does that make sense? If I can make that sigma squared, I had to put a radical there, and that's really what's going on right here. Okay, so this standardizing procedure is exactly the same thing we did in 8.1. Okay, now I am not assuming, and I'm not requiring you to memorize. That's a messy formula, yes? Okay, and a lot of the formulas that we've been seeing can be kind of messy, and if we're working on 8.1 to 8.2 to 8.3 to 8.4 to 8.5, and there's a different formula for each one of those sections, is it going to be easy for you to make a mistake? Yeah. Okay. So I'm not taking the approach that all this stuff needs to be built into your mind and you can't forget it. Okay. So going into the test on Thursday, if you don't have your notes, you'll at least have these formulas. Does that make sense? I'll provide this stuff for you. Okay. I would much rather you concentrate on how do we do this stuff instead of what is the formula. Okay. So here says the confidence interval. Then basically what's going on here is that this formula. Okay, and we did this previously in 8.1. Basically, what I want to do here is solve this formula for mu sub 1 minus mu sub 2. Mu sub 1 minus mu sub 2. Okay? So when we cross multiply, we do all that kind of stuff, and this is what we get. Okay? And there's a couple different ways that we can write this, and I've got ultimately 3 different ways of writing our confidence interval. Okay? Our confidence interval can be x bar minus y bar plus or minus the z-score, okay, of alpha over 2, okay, sub alpha over 2, which just tells us, like, if we're looking at 95%, 99%, 90%, whatever it may be, okay? So that's that 1.64 number, 1.96 number, 2.58 number if we're looking at 90, 95, and 90, was it 99%, okay? And then times that square root of the variance from population 1 divided by the size plus in the variance of population 2 divided by its size, okay? Reconfiguring that a little bit, okay? We can relabel we're not relabel, but redefine this here. And this is the same thing we did in 8.1, 8.2, 8.3. That's our margin of error, okay? So we can actually call that E. So if I have x bar minus y bar plus or minus E, Well, that's going to generate this thing right there. Yes. Yes. Because of the z distribution here, because we know it's normally distributed, we will use the inverse norm function on this. Okay. Just like we talked about in 8.1, okay, if both m and n are large, which means for us, because of the critical value being 30 for the central limit theorem, okay, if our m and n are both 30 or greater, the central limit theorem implies that our confidence interval is valid even without the assumption of normal population. And basically all that says is if we go through and we see that we've got two samples and we know they're both greater than 30, then the problem does not have to say that the population is normal. Does that make sense? Okay. If those m's and n's are not greater than 30, the author has to tell us, hey, this population was normal. Okay? Does that make sense? Okay. You guys remember that flow chart we did with the z-scores and t-scores trying to decide which one to use? It's the same thing. Okay? Still have to use that here. It says, furthermore, use of sample variances, variance sub 1 and variance sub 2 in the standardized variable z yields a valid interval in which variance sub 1 and variance sub 2 replace sigma sub 1 or sigma squared sub 1 and sigma squared sub 2 respectively. And that's what you guys said earlier. Okay, if we don't have the population standard deviation at our disposal, the best thing that we can do is replace the population standard deviation or the population variance with the sample standard deviation or the sample variance. Is that okay with everybody? And that should be consistent with what we've talked about all year long. If you don't have the population, what's the next best thing? It's the sample, right? Okay, so it's the data from the sample. So we'll just replace those things with it. So here's kind of what happened. Here's an example, and I've got all this stuff here. We read through it, but we didn't really. I'm not proving any of this stuff with you or anything like that. It's there for you to reference back to. I think the best thing that's going to happen for you to get used to this is just to run through some practice problems. Okay. I've talked about statistical packages before, like SSPS. Excel is a statistical package. Excel actually has you can go and just people build add-ons to Excel, so I can go download an add-on and upload it to Excel, and it gives me a bunch more functions and allows me to do a lot more data crunching and that kind of thing. This is this data here that's shown at the bottom on this table is a printout from something like SSPS or another one. You guys ever heard of Minitab? MATLAB? Okay. All right. So those are some things. Those are MATLAB actually. We don't purchase. I don't think we purchased it, but there's a version of MathXL that incorporates that data package. But regardless, this is a common-looking printout for a statistical package. Okay. Here it says an experiment carried out to study various characteristics of anchor. Let's just say bolts with a T. Resulted in 78 observations on shear strength of 3/8-inch diameter bolts and 88 observations on the strength of 1/2-inch diameter bolts. Okay, everybody know what a bolt is, right? Okay, what's shear strength? Anybody ever been working on a car or something like that, and you put a wrench on it or a socket and you start torquing it, and the head of the bolt snaps off? You ever do that? Okay. That's referred the breaking point of that head of that bolt is referred to as the shear strength. Okay. It's basically the strength at which the bolt fails. Does that make sense? okay, and breaks. So the table here says that if we're looking at the 3/8 inch diameter, and here is our 1/2 inch diameter, okay? We go through here, we see let me zoom in on this, and I just want to kind of describe per our formula what these values are. Would you guys agree that that is a sample size for one of our populations? Okay, so I'm going to come up here and let's call that M. Is that okay with everybody? Okay, here's the mean. Okay, now this is the mean out of these 78. Does that make sense? X bar. Okay, now all these other things, okay, are, obviously your median. You've got your 5-number summary here. I would argue, and I'd have to look this up. I believe that's true mean. Okay, which I'd have to look up what this package is referring to that as, but we're not going to use that value. Standard deviation, okay, whether that is the standard deviation out of the population or it's out of the sample, I'm going to assume that's the sample standard deviation, so I'm going to call that S. I'm going to call it S sub 1. Is that okay with everybody? Okay. And this is the standard error of the mean. We don't really need to worry about that at the moment. Come down here to variable. So this was all for variable X. I don't want to put a bar on there. Just variable X. This would be variable Y. Okay, they're independent. You can't have a 3/8 diameter bolt that is also a 1/2 diameter bolt, right? They're different. Okay. Our sample size here would be 88. Okay, our mean here, which we're going to call Y bar, is 7.14. Standard deviation we'll call S2. Okay, and that is then the information that we're going to use to make some decisions here. Okay, so we're going to calculate a confidence interval for the difference between the true average shear strength for 3/8 inch bolts, which we're going to say is mu sub 1, okay, and true average shear strength of 1/2 inch bolts, mu sub 2, using a 95% confidence level. Okay, so let's do a couple things here. If I say 95% confidence level, does anybody remember the z-score that attaches to that? Z sub alpha over 2 would equal what? 1.96. Okay. I am going to write my formula here, okay, as x bar minus y bar minus E less than mu1 minus mu2 less than x bar minus y bar plus E. And then to the side, I'm going to identify what is E. Remember, E is z sub alpha over 2, the square root. Okay, now, thinking about this, does the order of these things matter right here underneath the square root? No, addition is commutative, right? The only thing that it's saying is that the variance that you use for the 3/8 bolt has to divide by the number of 3/8 bolts. Does it make sense? You would not want this to be the variance from 3/8 inch bolts and this be the number of 1/2 inch bolts. Okay? So just make sure that those two things align. So I'm going to say, S1 squared over M plus S sub 2 squared over N. And now just plug the information that we gained out of our table up here. Okay, so you guys said z sub alpha over 2, that's going to be a 1.96 value, right? Square root then, okay? The standard deviation is 1.3 for these bolts, okay? Now just understand that, and this is basically because of this statistical package that generated this table, and I would argue that most are like this, that it produces the standard deviation. It doesn't give me the variance, right? So I need to make sure that that 1.3 gets what? I want to square that, right? Okay. If it would say variance here, then I wouldn't square it. Okay. But this thing here is either your, however you want to view it, standard deviation squared or just your variance. So I'm going to go 1.3 squared. Okay. And I'll divide that then by 78. And I'll add to that, okay, the standard deviation of the 1/2 inch diameter bolts, which is 1.68. And then I'll divide that by 88. Is that okay with everybody? Okay. So let's figure out what E is. .96 square root 1.3. I would just use, like, I prefer this calculator because if I'm typing this on my TI 8384, underneath the square root, you've just got some nasty order of operations that, based on parentheses, might get mixed up on a kind of cheaper calculator. Okay. So we're getting that value. Oh, I didn't square this one. So 0.454. 0.454. E. .454. Okay. So that is what we're going to subtract from x bar minus y bar, and it's what we're going to add to x bar minus y bar. Okay. Well, this is the whole thing that we're doing. That's the difference in the means, right? So I'm going to come up here, and I'm going to look at the mean of 4.25. So 4.25 minus, and a couple different ways you can. I would probably come to the side actually and do this. What is x bar minus y bar? I would just figure that out first. 4.25 minus 7.14. .25 minus 7.14, negative 2.89, right? Negative 2.89. So now this thing here becomes negative 2.89. We'll subtract 0.454 from that. That'll be less than mu sub 1 minus mu sub 2. Less than, okay, now negative 2.89 plus 0.454. So I'm going to say negative 2.89 minus E. So this number here becomes negative 3.344 is less than mu sub 1 minus mu sub 2, less than, add this, so 2.436. 436. Negative 2.436. Okay, that's my confidence interval. kind of weird, but would you guys agree that these two things here, so no matter what mu sub 1 minus mu sub 2 is, would you agree that it is always negative? Because of that being negative and that being negative, this value here has got to be negative. Does that make sense? Okay. So mu sub 1 minus mu sub 2 has to be less than 0. Is everybody okay with that? That's what it means by mu sub 1 minus mu sub 2 to be negative. Okay, and we're seeing that we know it has to be negative because it has to fall between these two numbers that we just found. Okay, well, if I do a little bit of algebra here, real easy algebra, add mu sub 2 to both sides. If I add mu sub 2 to both sides, you get that right there, correct? So what does that tell us? That tells us the mean of population 1, which was our 3/8" bolts, right, is less than the mean of population 2. Does that kind of make sense to me, or to you? To me, it's telling me that the shear strength for population 1 is less than that of the shear strength for population 2. Does that make sense to everybody? And think about it. Does that make sense? If I have a 3/8" bolt, which one would be easier to break, 3/8" bolt or a 1/2" bolt? Which one's thinner? 3/8 is thinner, right? Okay, so its shear strength is probably less than the 1/2" bolt, and that's what this is kind of describing to us. Does that kind of make sense to everybody? Now because of the confidence interval we chose, we're saying that we're 95% confident that mu1 is less than mu2. Okay, with that interval of -3.34 to -2.436. Okay, so we're saying there that we're 95% confident that the difference between those two populations is between those two values. Is that all right with everybody? Okay. Again, I'm more concerned with that final conclusion. Sample 1 minus sample 2, their sample means, leads us to saying that the population mean of the 3/8 bolts is less than the population mean of the 1/2" bolts. Is that all right, everybody? And that's usually what happens. So we talk about these statistical packages, and we could do this in Excel. I've chosen not to show you this yet, okay? But there are some commands in Excel that I can just type in. I can hit a command, and it will tell me what the confidence interval is, and it will skip over a lot of this work, okay? There are a lot of programs where I just type in my raw data, and it generates tables that has all the information that I need in it. Does that make sense? And then I, as the researcher, have to decipher, well, what does that process data mean to me as a researcher? It means basically, well, we've got that box of mu1 less than mu2. That's what the statistician, the researcher is looking for. That's the conclusion that we're interested in. Okay. We'll pick up there tomorrow. And like I said, test on Thursday. Next week, if you have any interest, next week we're getting into hypothesis testing, which is going to be a tool, again, that allows us to either validate or reject claims. Okay, I might be working on a line at P&G, and I have a claim that this machine is not filling these bottles to the predefined amount, okay, based on the samples that we're collecting. So hypothesis testing would let me to check that, okay, and to make that conclusion or to reject that conclusion. So that's where we're going with this stuff. In hypothesis testing, much of what we're doing now over Chapter 8 is used again in Chapter 9. Okay, so that's the reason why I've spent a lot of time on Chapter 8 with you.